So I'm introducing Kristin Persson, who is the Daniel M. Tellep Distinguished Professor at UC Berkeley and a senior faculty scientist at Berkeley Lab. Kristin is also the director and founder of the Materials Project, which is a world-leading resource for materials data and design. Under Persson's directorship since 2011, the Materials Project has become the most widely used open access repository of information on inorganic materials in the world. And the database holds millions of properties on hundreds of thousands of crystalline structures and molecules, information that is primarily produced here at NERSC. So please welcome Kristin Persson.
Thanks so much for the very kind introduction. It's very nice to be here. NERSC has been a critical partner to the Materials Project since the very beginning. So I'm happy to come and talk to you about where we are today and give some credit to people who've been there for the road. So it's pretty timely. Here we go. I hope I didn't press the button. To talk about machine learning and AI and what we need to do machine learning and AI today. So just a few weeks ago, the Nobel Prizes, quite unusual. They both in physics and chemistry recognized the use of AI ML in both physics and for protein data, for protein structure prediction. So obviously algorithmic training and algorithmic development has a big role in this, but I would like to highlight the role of data as well. The efforts that led to the chemistry prize are reliant on the algorithmic development, but also on decades of collection and curation of protein structure data. So to talk about that, the AlphaFold architecture trained exclusively first on the protein data bank and reached high accuracy with that, and then even higher with UniClus 30 sequences. And a little bit of I don't know how much you know about the protein data bank, but it was established in 1971 at the Brookhaven National Laboratory and then expanded in 2003 to the Worldwide Protein Data Bank. And not only do they curate protein structures that are delivered from all over the world, they also deposit the data process and they distribute it to the world. And as somebody who's been doing that now for a decade and a bit, I know how much work goes into it. And from the perspective of the Materials Project, these are just structures. The Materials Project is trying to do structures and properties of materials. So we're adding another dimension. So the functionality of materials is part of the Materials Project mandate as well. So I think it's fair to say this is a slide I use quite a bit because this is what I show my students when they want to join my group, and they all want to do machine learning today, not surprisingly. So I give them a little bit of a riot act to begin with. And I say, yeah, in order to drive that beautiful Ferrari that you really want to do, you're going to have to produce the fuel first. And in many cases, that fuel does not exist in physical sciences. We have to calculate properties. We have to look through the literature. We have to write our own text mining tools to actually extract that information. And in many cases, our papers, the way we write them, they're not meant to be extractable. They're meant to tell a story. And then if there's one message I would like to, and I keep saying it, that we should change the way we publish our data today because it is overdue the way we use it. It's not just stories anymore. So in terms of the material science, so we've talked about proteins, we talked generally. The material science, we haven't been very good at this. We haven't been very good at taking care of our data. We've been lots less good at it than the biologists and the protein people. So we started looking at this in the early days of the Materials Project because we needed benchmarks for our calculations. Yes, EFT and density functional thing. I heard somebody say it was low accuracy. Oh, very sad. It's not that bad. It's actually in many cases better than 2 different experiments done on the same material. So, and those are the gold standard data points that we compare to. When we calculate the elastic tensor of a material, what do we compare it to make sure that we're doing the right thing with DFT? Because we still have to tune numerical parameters and stuff. Well, we look at experimental data, and very often we find two data points on the same, which is unusual. Then they tend to differ more than our estimated error bar is. So to give you a sense, elastic tensors, maybe 200 compounds, or we can find in the open literature, and there are hundreds of thousands, order of magnitude, unique crystalline structures known in the world, inorganic ones. Dielectric constant is just as sad, species 400. If you go to superconducting temperature, you get a bit better. Can you guess why? Any sense? Huh? Less motion. Ah, interesting. I mean, I don't know the answers. You could be right, but I'm hypothesizing that if you measure a high superconducting temperature, you have a discovery of a high TC material, and there you get a cool paper. If I measure an elastic tensor, I'd have to have a really special one to get a good. So nobody's going to give you a cool publication for measuring elastic tensor. And by the way, it's really hard, much harder than measuring the superconducting temperature, because you have to have a single crystal, and making that single crystal is like 5 groups in the world who does these days. So it's really hard, surprisingly, even though it's an incredibly fundamental property of materials. And we use it for a lot of things. If you want to design a new iPhone or anything, you kind of have to know how things change, how crystal structures change when you tug at them or you strain them in some direction. So by and large, we're not going to get there with experimental data, and we haven't been very good at taking care of it either, because this is us and my graduate students and other groups like filtering through the literature and trying to find these precious gold nuggets of gold. Okay, so here comes computing. And that's very exciting, because in the early 2000s, I was a graduate student in 1996 in Stockholm. So in the early 2000s, I arrived in the United States, and that was just at the cusp of what high-speed computing was starting. Like we were starting to see the big clusters being used in this way. And that means that we could use things like density functional theory to actually calculate materials properties loads faster than we can measure them. We don't have to make the material. We don't have to make sure it's phase pure and whatever form it needs to be in order for us to measure that property. So that was a game changer for material science. It now gave us another way of accessing those hard-earned properties. So and a little bit of history, and that involves NERSC, right? So fast forward now, I arrived in 2001 to the United States. In 2008, I came to the lab. And in 2010, I wrote this LDRD called Accelerated Materials Design. And it's kind of cool, because there's like, okay, you can compute things, which was called the QMDB in those early days. But then I said, oh, we should have like, the user facilities, and we should get data from those people. Then that should be part of the database too. And the ALS should get data in there. We're still working on that. But the first part of those 3 pillars has actually been done. We are working, or we have band structure, we have density states, we have elastic properties shown on the crystal structures in the materials project, and they are being disseminated all over the world. I had a little iPhone there to show that, oh, yes, we can do that. And then I think my postdoc, Michael Coker, who some of you have been here a long time, may remember. Yeah. He won the mobility prize for this iPhone app that he did on the early versions of the materials project. And I thought, given that there was somebody who asked about, like, I can't parallelize my code very well, that was us back in the day. So the little nugget there, that's an email from 2012 where NERSC was really kind to us and let us use blocks of computing, reservation systems, so that because we didn't do very well with like actually getting parallelized versions. So we just had to use one node at a time. We still kind of do that to some degree, but like one node at a time for some amount of fixed time. So we got reservations in the early days. So thank you so much. That really helps. I just have a lot of sympathy with people whose codes don't run very well on the kind of architectures that we have. So in 2011, also a little bit of history, and that might be fun for you guys. This was a slide on the materials project infrastructure, the software infrastructure. And there's some people there that you might see, like Kathy Yellick is part of that slide, David Skinner, Shreyas Kolia, Dan Gunter, and F is there. So, it was nice to see. And then in 2012, we got one of the 5 coveted centers that came out of the Materials Genome Initiative, landed here in Berkeley with $2 million a year, and we're now a core program in the Materials Science Division. So without NERSC's help, without critical involvement from the NERSC team in the early days, I don't think we would have gotten there. So I'm really, really grateful. This is indeed a good charging pointer. Oh, ooh, okay, now I went too fast. Okay, here we are. So these are the three pillars, or the four pillars really, about the three sort of missions that we had in the early days in the proposal to accelerate materials discovery through giving this amount of data to people. And I'll show you some examples of how this actually has worked out. With the NERSC's help and all the people that were part of the team, Shreyas is still part of the team, to scale those computations as well as we can over the NERSC architectures that keep changing, of course, and disseminate those tools and that data to the broader community. And that is an aspect that we have now. We started out doing that at NERSC, but we have moved most of that into the cloud because that is just a more robust 24/7 uptime vehicle for us, given that we have, it's grown a lot since the early days. The amount of code that we've written in-house to manage this is not small. You would think that this is not that hard, right? You just have your script and you run your calculations and here we go, right? We get lots of data. And there are lots of groups in the world that do this. They have a script, they run some stuff, they get some data. But if you want to be the world leading data repository, you have lots of eyes on that data. It needs to be good data. It needs to be checked data. You need to make sure it has all the bells and whistles of it's converged. We know exactly what happened with it. We can now build it into our infrastructure. We can compare it to other data items. So it's not a single point living in space, right? We can see, is this elastic tensor similar to other things with similar chemistry? So all of these codes speak to that to some degree. Fireworks is a workflow code, quite agnostic to what kind of workflow you're writing. Custodian catches errors, so we don't have to do start stop so much. So we actually, it's like seamlessly can apply those recipes for when things go wrong. That was also really important that we can talk to an outside mother node or something. So we need communication, which is why we can't deal with really slim architectures like the one at Oak Ridge. We've tried, it's impossible. It's really inefficient. We thank you very much, Titan, for all the time. We didn't use it. Atomate 2 and Atomate kind of combines Pymagen, which is the I/O code, with Fireworks. Magma, Emmet, and the API are all about building the data and delivering it to the community. And then we have a bunch of things that have to do with the website. So most of these we've written ourselves in one form or the other. And there was no roadmap. There was nothing like the materials project that existed when we started. So a lot of these have become community standards. Python was kind of new-ish when we started in 2010, 2011 for the things we were doing. MongoDB was certainly new, and I still remember when Dan Gunter told me I should use it. We have a good partnership with the MongoDB people. They like us. We used it for a long time. And a lot of other people have followed suit because we sort of became industry standard when it came to how do you do a good community, or how do you build a database robustly. Something that may confuse or surprise people, like, oh, you've been running since 2011, lots of data, huh? Yes, lots of data, but the most important isn't just lots of data, but also how accurate it is. So we keep recomputing things. When new functionals or better methods, faster computers, better parameters become available in high throughput, we recompute things when a better pseudopotential becomes available. So there is very little data. I think I would almost guess none left of the earliest versions of 2011. So all of the things you see today are things. So we keep sort of upping the bar, because if we were the same in 2011, we would be obsolete. But the field moves pretty quickly. So when people compute something today in their own labs, we need to be as good, if not better than that. We also have a deprecation process. That's also something that's important. If you're delivering data to the whole world and somebody's writing a paper on the version of the database that's 2 years old, that's not unusual. You download the data through the API, you analyze it, you do something, and then suddenly a year later, then that paper exists. And if that's not the data that exists when somebody logs into the website, what do? Well, that data is not still available with all the sort of provenance available to it. So people can go back and look, and they can download through the API versions of the databases and compare to why did they get, or what kind of results they should be looking at. So here's what the data infrastructure looks like today. We still have a lot of that code and we still keep updating it. We run most of our production at NERSC, but also in other places. We store it in MongoDB. What has changed a little bit since the early days is that, first of all, we have a great partnership with OFT. We get DUIs for every single one of our materials. That's really important for provenance. And we have partnered more and more with cloud and cloud providers to make sure that we don't have to do the heavy lifting of authenticating our users, of maintaining uptime for our data, making sure that our API can serve pretty much any user, anytime, 24/7, 365 days a year. So all of that is now, most of our data is an open data at AWS, and we have a really nice partnership with those people as well. So we think that's useful. We've also, I'll get back to the research. Here we are. So a little bit, so I've talked about data production. This is an example of our data of workflows, and this is the one particularly on elastic tensors. That was one of our earliest data sets that we keep adding to. And again, really hard to do from measurements. So let's see, that's one of these property data sets. And you might be able to see, and this is sort of, it may be important for materials in particular, the lowest one, the sort of gray bottom one, that's structures. So that would compare to the protein data bank. That's just the structures, but everything above that is properties. So for us, it's very important that you can tie a property to an underlying crystal structure and chemistry, because that's where a lot of people want to do machine learning, because they want to come up with new materials, new structures. And that means that you have to do some machine learning involving, well, how does the property correlate with structure and chemistry? So it's about functionality as much as it is about structure. So a lot of the compute, a lot of our efforts have become about developing these workflows for materials properties and not the structures for computing research. What have people used it for? So the first original 6,000 elastic tensors, and remember there were about 200 in the open literature. So the first data set that we fielded to the public, 6,000, what has it been used for? Well, for example, here are some examples of people using it to machine learn bulk modulus values, shear modulus values, which again is how a material deforms under various influences, to identify materials with high hardness. So things like could be used for coatings. These people also made these materials and show that indeed these machine learned predictions on top of our data was indeed correct, and they could make new materials from that. Here's another one, again, using the elastic tensor data set, but also band gaps to do machine learn approximate Goodbye temperatures and photoluminescent yields so that it can come up with new phosphor materials, so materials for lighting, energy efficient lighting. And you might notice here that the original paper on the original data set, 6,000 hard-earned elastic tensors went into scientific data. You can look up what the impact factor of scientific data. It's not bad, but it's not JAX and it's not Nature Communications. So the people who make a discovery on top of that data, going back to the Nobel Prize in chemistry, they tend to get more bang for their buck than the people who sort of curated and produced and delivered that data. That's fine. I'm really happy that we can support that. Here are other examples of what people do with the data. So people use it just for filtering. They just, oh, I just want to filter materials that have good stability, these kinds of vibrations, that kind of elastic tensor. So those are the kind of funnels you see over there. Some of the big players now in industry, we're very happy to see them, really large companies like Microsoft, like Google, like Meta. Even TikTok, I think, is running LAMPS, which is really strange to me. But those big companies, they are taking our workflows, they're taking our Python codes for IO, they're using our data as their first training set. So the genome, which some of you may have heard, that made quite a splash last year, December 2023. The genome data sets delivered 380,000 new structures to the world. Their original first training was all the materials project. And all of the things you see over there, going from just structures to the Open Catalyst project. They also used our workflows. I hope you appreciate the little info that I stole from Intel, that empty inside. So all of these are extrapolations or where they started out with some inspiration from what we do, either in terms of data, software, workflows. So it is an accelerator, an innovation multiplier, I've heard that one should call it. And that's great, that's what we set out to do. One thing we did not set out to do, and was actually a bit of a serendipitous win, was that for provenance, we saved all the relaxation trajectories. So again, data that we calculated at NERSC. We saved all the little force energy pairs that, in order to find the ground state of the crystal structure. And we saved it because we wanted to give people, it's like, hey, we actually did the work. These things are relaxed. They're looking good, right? Just for confidence and provenance. Well, people do amazing stuff with data. So here you can all see the organization. You can go on the website and see all the different tasks of all the different materials that we've done. It's pretty impressive. So what did people do with this exciting data when they had access to it? So 10 years later, if I can advance this, here we go. 10 years later, 2018, people started realizing, that's a lot of force energy data. What if I I reverse engineer the Schrodinger equation, and I build a machine learning potential, a universal potential, and now hexaacid can take the derivative of these energies, right? All kinds of nice derivatives. We can calculate the elastic tensor, the vibrations, the phonons. So all of the machine learning potentials that you see there that have been really making quite an entry into material science today, all the way to the MACE Foundation model, which I don't think is published quite yet, but already has like 250 citations after a half a year. Because people are already using them. They're so excited. They can now run much longer trajectories with ab initio accuracy as long as you're within the training set. That's of course very important. But all of these were trained on the materials project relaxation data that we had 10 years. So the value of saving the data, value of curating the data and giving confidence in the data cannot be overstated. Here's the MACE Foundation model and all the different wonderful material properties that it can calculate. And over there you see something that we could not do a few years ago. It's the simulation of a lithium solid state lithium battery. We have lithium metal up there and the solid state conductor. And what you may not appreciate, but I think it's amazing, is that with ab initio accuracy, I can show how that interface oscillates. That we could not do. That was impossible. And always thanks again to these that they're on. So this is the idea, right? We want new materials. We want new materials for all kinds of technologies. We want new materials for quantum computing too. I heard people talking about that as well. As far as I understand, being an ex-director of the Molecular Foundry, there's a lot of exciting research, and we do need better materials for coherence, for keeping the coherence of those materials, right? For enabling quantum computing. So we now have new ways of doing this, going from Thomas Edison, who really gave the name of Edisonian research, so coming up with new materials, to being a little bit closer to Tony Stark in Iron Man, if you remember that scene where he basically synthesizes a material in a few seconds and then tests it, which we can't do, unfortunately. But I would love it. So here are some materials that we have, just like the NatureCom and the JAX paper that we have predicted in-house with specific functionality, from carbon capture to magnetocaloric, that's for solid state refrigeration, thermoelectrics, harvesting our waste heat. So all these wonderful materials, I can't say if these are going to be applicable or they're going to be commercialized, but at least they give them candidates. They do work as they were predicted. And the materials project has now changed a few times. We keep trying to innovate on the website to make it as accessible and educational as possible, because we want to reach people that are not just theorists and computational people. We want experimentalists to go in there too. They're actually the people, most of the material sciences in the world. So that's an important part. If you look at the number of papers that cite the materials project, every day it's 5 papers published every day that cite the materials project. And 2 of them today are for machine learning. So it's a rapidly rising number of papers. We also were very happy that we were inducted as one of the, I think now 7 Office of Science data centers. So this is something that the Office of Science does when they feel like, okay, we have a leader in data for one of our domains. They then send you another form with lots of things that you have to be compliant with. But once we show that, you can be one of their left pure data resources. So I think we're very good at this at LBNL, right? We have quite a few of them. So this is really something we're passionate about. In the risk of upsetting people, we dared to compare ourselves to the interest of other databases. This is always dangerous, but just to give you a sense how much the interest in the Materials project has increased since 2021. So it really is not just stagnant, but it's a growing interest in the community. And I think this is one of my last slides. They're used all over the world. We currently we reached a few weeks ago 500,000 registered users from all over the world. We're growing exponentially, serving 168 countries. I think every day about 300 new people log on and become new users. That's every day. And we are serving hundreds of millions of API requests. And I really want to thank my group, the Materials Project team, NERSC, for all of your help since the very beginning, and these 4 people here, Tyler, Patrick, Aaron, and Roshi, who are my 4 software engineers, without whom I could not do any of the things that I've been talking about today, because they make the whole thing work. So with that, thank you so much, and I'll be happy to take questions.
A great talk. I enjoyed it. So you mentioned about the number of papers per day citing the Materials project. But do you have other ways that you kind of show value that the project? You know, you talk to it's the data, and then there's many derivative products above that that may even be maybe steps away for you. So how do you measure that? How do you communicate that?
That's a great question, and something that I wish I could do more of. It's hard for us to do it automatically, right? This is one of the few ways that we can track it. Most of the other stories that I showed you, like here's where they took the data set. We have to go really down all those citations and see what the paper did, and we do that manually. So I could, if I had the money, I would hire a full-time person on just checking that. And I know some of the big centers in the United States, they literally have a full-time person who checks on what is the impact of your effort, because I mean it's worth a lot, right? To show people how the taxpayers' dollars are being spent.
So I know you had at least some effort, I don't think you talked about in this context, of literature search, that natural language processing thing that became Google or COVID Scholar. But yep. Is that one thing that you use for this as well?
So we haven't actually used it for tracking, because I think a lot of the value, so you can certainly pick out things in that way. To really find out what they did, I think we would have to spend more effort on it. Currently, we had one effort on synthesis. So all the synthesis recipes are in the Materials project now. That was one of the efforts. Yeah, the another effort was trying to track when people came up with a new material. Those were relatively easy things to text mine and to get from the literature. That field is moving so incredibly hard, we can't keep up with it anymore. So my group has stopped doing anything on that aspect, because my 4 students wouldn't be able to publish because they couldn't keep up with all the enormous efforts in text mining that's being done around the world, and including in the scientific. When we did those early things, it was pretty early for scientific literature. It's not early anymore. Otherwise, I do think it's a great idea for getting curation, but having as a research project is rough.
Hi. Thanks a lot. It's great talk and really enjoyed. So I have a question. So I'm interested in what is your roadmap for MP project, because you listed 100,000 or 2,000. I don't know. You have compound. It will be like ending at certain days, right? So what is things you can do more? This is my first question. I have second question is, so to look at any DOE funding or any funding to keep supporting this database. Because I thought you guys started as a research project, but now it's like the database is used to answer questions for other scientists, right? So it's becoming kind of tools. So how you foresee keep going?
Okay, great. I'll try to remember both of them. So the first question was, what's the roadmap? And so the good news for us is that even if we run out of compounds, which we really won't, because in the sense that you can always start doing substitution. So we already have a fair amount of what we call theoretical compounds in there. So trying to innovate on new materials and substitute in. There's also all the solid solutions, like adding defects to materials. So just on the structure and the chemistry, there's a whole world we have touched a little bit, but not nearly as much as we could. And then all the properties. We haven't calculated all the properties for all those materials. We've done 14,000 elastic tensor. That's not even, because again, we're sort of limited by compute and by people's time. People have to at least look over the thing and then to build the data and all that. So what we're now using at, okay, 14,000, and then we have universal machine learning potentials and machine learning to try to fill out the rest of the space. But all the properties that you saw here, they're not, we haven't filled the whole space, and we have certainly more properties that we can calculate. So there's on just that aspect, there's tons more. We run on everything we can find. So there's lots left. That's not one thing that worries me. On the other side, so the good news is that BES have realized that what they need, what's needed. So we've spent some time making sure that the 4 software engineers that I have up there, that you could argue that is not really doing MSD core science, like that kind of stuff, but they recognize the value of them. So of the 3 million that I now, so I've been funded the whole time. That's also a great thing, right? That's been a core program since 2017. That's when they went from a limited center to inducting into something that doesn't have an end date unless the program manager thinks you're done. So we have had continuous funding. It's now up to 3 million a year. 2 million of those go to those 4 staff. As we know, expensive at a national lab, but they understand that they have understood the reason that we have those 4 staff. I personally think that in combining your question 1 and question 2, where is the roadmap for the materials? Well, I do think that it should separate what is the innovation part in terms of new workflows for new materials and the user-driven aspect. Where should this go? It should become some sort of user facility or tied to user facility, because that part is very much it's innovative in the interdisciplinary realm between CS and cloud and materials domain, but it is a little awkward as a BES MSD program, of course it is. But maybe that's what interdisciplinary is. It's always a little awkward at the beginning. So I don't know, but I would love to partner with BES and DOE, and where should the first maybe software domain user facility sit? They're all centered around hardware.